Okay, good afternoon. Let's begin the all-important chapter on bipolar junction transistors, BJTs. The rest of our class, except for the final week, we'll talk about MOSFETs, but until then, for the next 3 weeks, it's all BJTs. Okay, so let's see. First up, it's right here. Bipolar junction transistors. This, in fact, is the first semiconductor device that was ever created and presented. Right? The first semiconductor transistor presented in 1947 was the germanium point contact transistor. I have a picture of it here, I think, in a couple of slides. Let's see. Okay, just making sure sharing the right slides. All right, so as you can see, the BJT is a stacked layer of three P-type and N-type semiconductor materials. It's a sandwich structure. So you could have a sandwich structure of PNP, or you could have a sandwich structure of NPN. Okay, and that's where the name of these two transistors come from. Either it's a PNP transistor or it's an NPN transistor. Symbols for both are shown right here. If the arrow is pointing out on this terminal, it's a NPN transistor. If the arrow is pointing in, so this is pointing in, this is pointing out. If it's pointing in, it's a PNP transistor. If it's pointing out, it's an NPN transistor. Okay. Most of our discussion will relate to or will specify using NPN transistors. Okay. But the exact operation for both is the same. The only difference is electrons and holes will switch places. Okay. Other than that, everything else remains the same. Here is an actual slice, here's a slice of an actual BJT. So you have these in your lab kits, the tiny epoxy packaging with 3 terminals coming out. You saw that with the JFET. Some of you may have skipped over the JFET, but you have that JFET and the transistor in your lab kits. Coincidentally, the packaging for both is exactly the same. So black epoxy packaging. When you slice it, this is what you see in there. Okay. And the transistor is not even that. If we zoom in, the transistor is like right on here. Really, really small. What you see on the backside is the contact, as an aluminum metal contact, making contact with the collector terminal. Okay, and the rest of it is just epoxy capsule. Okay. Here again is a top view of an integrated transistor. Top view of BJT on a silicon wafer. So we look at both the top and side views. For explanation purposes, we can use either or. For the most part, we do use side views. Just makes it easier. Okay. Here's the construction and the terminals. Okay. So again, this is the side view. And the dimensions are exaggerated. Okay. Dimensions are exaggerated. What do we see? This is an NPN transistor. There's a thin P-type material between the two N-type materials. So it's an NPN transistor. The largest region is known as the collector, indicated by the C. In the middle, you have the base, indicated by B. And then lastly, you have the emitter, indicated by the E. On the symbol, the emitter is noted by the arrow. Okay, so the arrow that I pointed out, whether it points out or in, that notes the emitter terminal. Okay, similar to something on the JFET. Now, when you have three regions connected back to back, the first obvious thing we can think of is, well, these are two back-to-back PN junction diodes, right? And that is true. These are two back-to-back PN junctions, but they are not diodes, or they will not function like true diodes. Okay. All right. Okay, so the differences come from the fact that the construction, the physical construction of the device and the design of these devices is completely different from a normal PN junction diode. In a normal PN junction diode, we might have some symmetry between the dimensions and the doping profiles. In a BJT, the collector is by far the largest structure. Okay, it's by far the largest structure. The base is inside the collector. However, it is very, very thin. Okay, so the depth, if you're looking at it from the top, the base is inside the collector, but it's very, very thin in the Z direction. So it is very thin. Also, it is very, very lightly doped. And these two put together result in the function of the BJT. Okay, the base is very thin, plus it is very lightly doped, meaning there are not enough charge carriers. And then lastly, we have the emitter. If you are looking at it from the top, you have the collector. Inside the collector, we have the base. And inside the base, we have the emitter. Now, the emitter, as a two-dimensional structure, looking at it from the top, is encapsulated within the base. However, it is very heavily doped. Okay, so there's an excess of charge carriers in the emitter. Okay, very heavily doped. So as it pertains to the size, as a two-dimensional structure, I would say collector is greater than the base, which is greater than the emitter. So I should have put this on the right. So two-dimensional measurements. Collector is greater than the base, greater than the emitter. However, the base is thinner than the other two. And in terms of doping, the emitter is higher than the collector, which is higher than the base. And I should amend my earlier statement. I should say all of these put together comprise the functioning of the BJT. Okay. So far, so good. Okay. Let's look at the physical construction. So in the physical construction, you have a three-dimensional layout. You also have the side view, and you can see You can see the physical construction of the base and the emitter right there. Okay. And again, of course, the dimensions are exaggerated. Wherever you see a N plus or a P plus, all it indicates is that it's more heavily doped. Sometimes to make a big difference, you would have, like, say, N, N plus, and N plus plus, or P, P plus, and P plus plus. And all it's indicating is that the level of doping is increasing. That's all it indicates. Okay, it doesn't mean anything else. All right, then let's talk about how and why this functions and how the design influences the collector. So let's say we have this NPN transistor, right? In this NPN transistor, what happens if you forward bias the collector and the base? It's an NPN transistor. So you have a P-type base structure in the middle, and you have an N-type on the collector. Let's say collector. So let's say what happens if you forward bias. Sorry, not forward bias. If you forward bias the emitter and the base. Okay. The emitter is very heavily doped. The base is very lightly doped. They form a P-N junction. So you have an N and a P-type material. You apply negative to the emitter, positive to the base, and you forward bias it. What happens? It acts like a diode. Absolutely. So it acts like a diode, and what happens? Emitter is N-type, has an excess of electrons. Base is P-type, majority carriers are holes. So they cross the junction. Once they cross the junction, the electrons and the holes recombine. Right? Recombination. Remember chapter 2, generation recombination. Everywhere there is an empty spot, some electrons will jump into that spot, recombine, send out excess energy. However, the number of electrons are coming into the base, and the number of holes that are available in there are far less in number. That's the difference between the heavy doping and the light doping. So now there's a whole bunch of electrons just hanging around in the base with nothing to do. That makes sense? A small amount of carriers recombine, small amount of carriers are flowing out of the base terminal. So the base current is very, very small, typically in microamps. Okay, just because the doping is low, so the number of holes is less, number of carriers is less. So the base current is very low. Emitter current is slightly higher. I wouldn't say slightly, it's actually a lot higher. So probably in milliamps compared to microamps. So thousands of times greater than the base current. But now these electrons are in the base, in the P-type structure with nothing to do. What happens now is if you collect these electrons, so if you apply a positive charge at the collector, the electrons that are hanging around in the base are able to cross over the junction. And the mechanism by which that happens is the reverse bias. So you have the base, which is P-type, you have the collector, which is N-type. If it's a P-type base structure, electrons are minority carriers. And if they're minority carriers and you reverse bias the second P-N junction, what happens to the minority carriers in P-type? They're able to cross over the junction because they're attracted by the positive. They are now reverse bias. And so now they're attracted by the positive voltage applied to the collector junction, and a heavy amount of current starts flowing out of the collector. And that's the function, that's the gist of how a BJT operates. You have an emitter-based junction, you forward bias that junction. When you forward bias the emitter-based junction, the charge carriers are going to go crossover into the base. Into the base, they are minority carriers. So the second junction, you reverse bias. When you reverse bias the second junction, the minority carriers which are excess in the base, are now able to cross over the second junction, and a huge amount of current starts flowing out of the collector. Okay, and that in short is also how amplification works. You inject a small amount of input into the base, but a large amount of carriers are coming from the biasing, meaning from the emitter, and then those electrons or the holes that are flowing out will take on the shape of the input base current or the base voltage. That's also the basic functioning principle of an amplifier. Okay. So let's take a pause. You think over that. Let me know if you have any questions. No questions? Everybody's in a hurry to leave. Let's again. Midterm every 2 weeks? A 50-minute? Oh, wow. Well, I guess my quizzes are easy then. Okay. All right. Anyway, we are almost at 4 p.m. So we're going to end class here today. We'll pick up here again on Wednesday.